From the Big Bang to the farthest reaches of the universe. Discover dying stars, black holes, cosmic collisions, and worlds beyond Earth. Explore mind-blowing facts, mysteries of our solar system, and the universe like never before. Before the beginning. Scientists call this state the singularity. Not a point in space, but the absence of space. Not a moment in time, but the absence of time. This isn't empty space, it's no space at all. And then, around 13.8 billion years ago, the universe suddenly appeared. Not like an explosion in space, but an expansion of space. The Big Bang. The first instant. Around 10 to the negative 36th power seconds after the beginning, the universe was smaller than an atom, but filled with unimaginable energy. Temperatures reached levels that no modern physics can fully describe. This wasn't a fireball, it was pure creation. Energy condensed into the building blocks of matter, quarks, electrons, and the forces that guide the cosmos. Gravity took shape, the strong force, the weak force, electromagnetism. The rules of reality switched on, one by one. Cosmic inflation. And then came one of the strangest events in cosmic history. Inflation. In an instant, the universe expanded faster than the speed of light. Galaxies didn't fly apart. Space itself stretched, dragging everything with it. Something smaller than a proton became larger than a galaxy. This is why the universe today looks smooth, uniform, and endless. Inflation took quantum ripples, tiny fluctuations in energy, and stretched them into the seeds of every galaxy we see today. The first light. For the first 380,000 years, the universe was too hot for atoms to exist. Electrons and protons were flying everywhere, scattering light in all directions. The entire universe glowed, but no light could escape. And then, the temperature dropped enough for the first atoms, mostly hydrogen, to form. Suddenly, light broke free. This ancient glow, the cosmic microwave background, is still traveling across space. It's the oldest photograph of the universe. The Cosmic Dark Ages. After the first light faded, the universe entered a long, silent era. No stars, no planets, just darkness. But inside massive clouds of hydrogen, gravity was slowly working. It was pulling matter together, squeezing it tighter and tighter, until finally, the first stars. Around 100 to 200 million years after the beginning, the universe lit up again. The first stars were nothing like today's. Huge, short-lived, brilliant. They fused hydrogen into heavier elements: carbon, oxygen, silicon, iron. In their final moments, these stars exploded and spread these elements across the cosmos. Everything, planets, oceans, life, was made from the ashes of these ancient giants. The birth of galaxies. Gravity pulled stars together into vast islands of light. Galaxies, spiral galaxies, elliptical galaxies, dwarfs and giants. Among them was one ordinary spiral, 13 billion years in the making, the Milky Way. Here, new stars were born, planetary systems formed, and eventually, one tiny blue planet appeared. From nothing to everything. So what began as a speck smaller than an atom became 2 trillion galaxies, each containing billions of stars, each star with worlds, moons, and possibilities. And now, billions of years later, a thinking species looks back and asks, how did it all begin? Where did we come from? Why is there something instead of nothing? We don't have all the answers. But we do know this. The atoms in your body were forged in stars that lived and died long before Earth existed. You are the universe, made conscious. From nothing to everything. From a silent void to a universe filled with life, light, and mysteries beyond imagination. And this story is still unfolding. New stars are forming right now. New worlds are being born, and our universe continues to expand into the unknown. What is dark matter? Let's start with dark matter. Back in the 1930s, astronomer Fritz Zwicky noticed something strange about galaxy clusters. They were moving too fast, so fast they should have flown apart. Yet something invisible was holding them together. Later, in the 1970s, Vera Rubin confirmed this by studying spiral galaxies. She found that stars at the edges were moving just as quickly as those near the center, which made no sense. The only explanation? There had to be an unseen mass providing extra gravity. That invisible glue was called dark matter. Today, scientists estimate that dark matter makes up 27% of the entire universe. Without it, galaxies would never have formed, and we probably wouldn't be here to ask these questions. Evidence for dark matter. Dark matter reveals itself in other ways too. It bends light around galaxies in a process called gravitational lensing, acting like a cosmic magnifying glass. It forms massive halos around galaxies and clusters that we can map using X-rays and radio waves. And in huge computer simulations, scientists tried to recreate the universe without dark matter, and the results were completely wrong. Galaxies didn't form. Cosmic structures didn't match what we observe. Only when dark matter was added did the simulation look like our universe. What could dark matter be? So what is dark matter actually made of? That's the million-dollar question. Some scientists think it could be exotic particles like WIMPs, weakly interacting massive particles. Others suggest axions, hypothetical ultralight particles. There are also theories that dark matter might not be particles at all, but something stranger, like modifications to gravity itself, or even hidden dimensions. Experiments deep underground, in particle accelerators, and even in space are all searching for answers. But so far, dark matter remains invisible. Enter dark energy. Now, if dark matter pulls things together, dark energy does the exact opposite. It pushes everything apart. In 1998, two teams of astronomers studying distant supernovae discovered something shocking. Instead of slowing down, the universe's expansion was accelerating. Something unknown was fighting against gravity on the largest scales, stretching space itself. That mysterious force was named dark energy. It makes up a staggering 68% of the universe. Think about that. The majority of the cosmos is being driven apart by something we don't understand. Theories of dark energy. So what is dark energy? One idea is that it's simply a property of space itself, a kind of cosmological constant, as Einstein once proposed. Empty space isn't really empty, it has energy. Another possibility is that dark energy is a dynamic field, sometimes called quintessence, which changes over time. Or maybe our understanding of gravity is incomplete, and what we call dark energy is actually a sign of new physics waiting to be discovered. Why it matters. Dark matter and dark energy aren't just abstract concepts. They determine the fate of the universe itself. If dark energy keeps accelerating, galaxies will drift so far apart that the night sky will eventually grow dark. If its strength changes, we could face entirely different cosmic endings, from a big rip to a big crunch. Understanding these forces could unlock the deepest truths about the universe, and maybe even reveal whether our cosmos is unique or just one of many. Dark matter and dark energy are reminders that the universe is still full of mystery. We may only see 5% of reality, but the hidden 95% shapes everything. Solving this puzzle could change not only how we see the universe, but how we see ourselves. How galaxies were first counted. Most of human history, people thought the Milky Way was the whole universe. That changed in 1924, when Edwin Hubble discovered that spiral nebulae were actually other galaxies. Fast forward to the 1990s. NASA points the Hubble Space Telescope at a tiny, empty patch of sky, a region no bigger than a grain of sand held at arm's length. The result? 10,000 galaxies packed into that tiny dot. This image, the Hubble Deep Field, changed everything. Astronomers estimated 100 to 200 billion galaxies in the observable universe. But that number didn't last long. The new galaxy count, trillions. In 2016, improved computer models and deeper sky surveys revealed something stunning. The universe might contain up to 2 trillion galaxies. Not millions, not billions, but 2 trillion. Most of them are small, faint dwarf galaxies, too dim for even Hubble to see. And with the James Webb Space Telescope looking back further than ever, this number may still be an underestimate. How galaxies form. Galaxies didn't appear fully formed. They began as tiny clouds of hydrogen and dark matter shortly after the Big Bang. Here's the process. Dark matter clumps first, creating invisible gravity wells. Gas falls into these wells. Gas cools and forms stars. Stars cluster into the first proto-galaxies. These early galaxies collide and merge to form bigger, more complex structures. Every galaxy today, including our own, is the result of billions of years of mergers and growth. The Milky Way is basically a cosmic Frankenstein. What's inside a galaxy? A typical galaxy contains hundreds of billions of stars, giant molecular clouds where new stars are born, nebulae, the colorful remains of exploded stars, massive black holes, often at the center, dark matter, making up 80 to 90% of the galaxy's mass, star clusters, gas clouds, dust lanes, and more. If you flew through a galaxy, you'd see everything from star nurseries to the skeletons of ancient suns. Galaxies are entire cosmic ecosystems. Dark matter, the invisible galaxy. Here's something wild. Most of every galaxy is invisible. Astronomers discovered that stars orbit way too fast for the visible mass to hold them together. They should fly apart. The solution? Dark matter halos, huge, spherical clouds of invisible matter surrounding galaxies. These halos stretch way beyond the visible galaxy, provide the gravity that holds everything together, make galaxies possible at all. Without dark matter, galaxies would never form. We wouldn't exist. Collisions, when galaxies meet. Galaxies aren't static. They move, collide, merge, and reshape each other. Every collision creates new stars, triggers enormous starbursts. Warps, spiral arms can form entirely new galaxies, and eventually, the Milky Way will collide with Andromeda. In about 4 to 5 billion years, the two will merge into a giant elliptical galaxy, Milkdromeda. Galactic collisions sound violent, but because stars are so far apart, almost none of them actually hit each other. It's more like two clouds passing through each other. Extreme galaxies. Let's explore some extremes of the universe. Smallest galaxies, dwarf spheroidals. Some contain only a few thousand stars, tiny islands of light. Largest galaxies, giant ellipticals. These monsters can contain 10 trillion stars and span millions of light years. Most active, starburst galaxies. They form stars hundreds of times faster than the Milky Way. Oldest galaxies seen by the JWST, some formed just 200 to 300 million years after the Big Bang. Each extreme galaxy tells a story about how the universe evolved. The future of galaxies. In the far future, star formation will slow, galaxies will drift apart, new stars will stop forming, the night sky will fade. Trillions of years from now, the universe will be a quiet place filled with dim, red dwarf stars and fading remnants of galaxies. But for now, the universe is bursting with energy, full of galaxies still growing, colliding, and shining. So, how many galaxies populate our universe? The truth is, we still don't know. Our best estimate is up to 2 trillion, but telescopes keep showing us more than we ever imagined. Every time we look deeper, every time we stare into the darkness, we find new galaxies staring back. And somewhere, in one of those trillions of galaxies, there may be someone asking the same question. How a star is born. Stars begin their lives in giant clouds of gas and dust, called nebulae. Gravity pulls everything inward, tighter, hotter, until the pressure becomes unbearable. And then, ignition. Nuclear fusion lights up the core. A new star is born. But from that moment on, a battle begins. Gravity tries to crush the star. Fusion pushes outward, fighting back. A star lives only as long as it can win this fight. A star's life depends on its mass. Not all stars live the same fate. Their mass decides everything: their brightness, their lifespan, and their death. There are 3 main types: low-mass stars, small, dim, long-lived; sun-like stars, stable, warm, middle-aged; massive stars, bright, short-lived monsters. And their endings couldn't be more different. The death of a low-mass star. A low-mass star burns its fuel extremely slowly. Billions, and billions, and billions of years. When it finally runs out of hydrogen, it slowly cools, shrinking into a white dwarf. No explosion, no flash, just a fading ember of what once was. Over trillions of years, that ember becomes a black dwarf, a star that has cooled into complete darkness. A quiet death, a cosmic whisper. The death of a sun-like star. But when a star like our sun begins to die, its ending is far more dramatic. When hydrogen runs low, the core contracts and heats up. The outer layers expand, and the star becomes a red giant, hundreds of times larger. One day, the sun will swell so large it could swallow Mercury, Venus, and possibly Earth. After this expansion, the star becomes unstable. Its outer layers peel away, drifting into space, forming a breathtaking planetary nebula, a glowing bubble of gas and color. At the center remains a white dwarf, glowing like a cosmic tombstone. This is the fate of our sun. The death of a massive star. But massive stars, they have a completely different destiny. They burn through their fuel violently, living fast and dying young. When they fuse elements heavier than iron, fusion suddenly stops giving energy. The core collapses in milliseconds. And then, boom, a supernova. One of the most powerful explosions in the universe. So bright it can outshine an entire galaxy. So energetic it forges gold, uranium, and the elements that make planets and life. A supernova is both destruction and creation. 2 possible aftermaths. 1. Neutron star. If the star isn't extremely massive, the collapse stops when protons and electrons merge into neutrons. The star becomes a neutron star. A teaspoon of its material weighs 1 billion tons. It spins at hundreds of times per second. It emits deadly beams of radiation, becoming a pulsar. Neutron stars are among the strangest objects in existence. 2. Black hole. But if the star is truly enormous, gravity wins beyond imagination. The core collapses past the point of no return. Space itself bends inward. A black hole is born, a region where time slows to a crawl, light cannot escape, and the laws of physics break down. The star's death becomes the creation of a cosmic abyss. Rare and exotic stellar deaths. Some stars have even stranger endings. Pair instability supernovae. Explosions so huge the star completely disintegrates, leaving nothing behind. Magnetars. Neutron stars with magnetic fields 1 trillion times stronger than Earth's. Hypernovae. The most powerful explosions ever observed, linked to gamma-ray bursts. The universe has no shortage of drama. Why stellar death matters. If stars didn't die, you wouldn't exist. Those explosions created the calcium in your bones, the iron in your blood, the oxygen you breathe, the silicon in your phone, every element heavier than helium. We are literally made of star debris, the ashes of long-dead suns. So the next time you look at the night sky, remember this: stars do die, but in their death, they give life to the universe. What is a black hole? A black hole is an object with gravity so intense that not even light can escape. They form when massive stars, at least 20 times the mass of our sun, exhaust their fuel and collapse under their own gravity. The result is a singularity, a point of infinite density where all the star's mass is compressed into zero volume. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape. It's the ultimate point of no return. Black holes vary in size. Stellar black holes can weigh from 5 to 50 times the mass of the sun. Supermassive black holes found at the centers of galaxies can reach billions of solar masses. For instance, Sagittarius A, the black hole at the center of our Milky Way, has a mass of about 4 million suns. Approaching the black hole. As you get closer, space and time begin to behave in strange ways. According to Einstein's theory of general relativity, gravity affects the flow of time. Near the event horizon, time slows down dramatically compared to the rest of the universe. From an outside observer's perspective, you would appear frozen in time, barely moving as you approach the horizon. But for you, time feels normal, ticking by as usual. You'd also notice gravitational lensing. Light from stars behind the black hole bends around it, forming distorted halo-like rings called Einstein rings. The universe looks like a surreal, warped painting. Spaghettification. As you get closer, tidal forces start to stretch you. The gravity at your feet is stronger than at your head, pulling you apart. Scientists call this spaghettification. You'd be elongated into a thin, noodle-like shape. In a stellar black hole, this could happen long before you reach the horizon. In a supermassive black hole, you might pass the event horizon without feeling much stretching initially. These forces are extreme, strong enough to tear apart entire planets. That's why black holes are often described as the universe's ultimate destroyers. Crossing the event horizon. Crossing the event horizon is the ultimate point of no return. Nothing inside can escape. Not light, not signals, not even information. From an outsider's perspective, you appear frozen, slowly fading away. Inside, however, your fall continues. Stars and galaxies outside warp and stretch, creating a bizarre, surreal panorama. Some physicists speculate that you might even see the future of the universe unfold in a few moments, but this remains theoretical. The event horizon is like a cosmic veil, separating the known universe from a region where gravity dominates all physics. The singularity. At the very center lies the singularity, a point of infinite density where the laws of physics as we know them break down. What happens here is unknown. Some theories suggest it could be a gateway to another universe or a wormhole. Others propose that information may be stored at the event horizon, leading to the famous black hole information paradox. Black holes are nature's ultimate laboratories. They allow scientists to study extreme gravity, time dilation, and even quantum effects in ways impossible elsewhere. Black hole mysteries. Despite decades of research, black holes still hold more questions than answers. Could they be portals to other dimensions? Could they store information about everything that has fallen into them? Scientists continue to debate and explore, using tools like gravitational wave detectors and space telescopes. Every black hole challenges our understanding of reality and may hold the key to understanding the universe itself. They teach us about extreme gravity, warped time, and perhaps even the birth of new universes. The Botas void, the great nothing. Imagine floating through space for hundreds of millions of light years and seeing absolutely nothing. No stars, no galaxies, just darkness. This is the Botas void, a cosmic desert over 700 million light years across. One of the largest known empty regions in the observable universe. Astronomers call it the Great Nothing, a place so vast if the Milky Way were inside it, we wouldn't see a single star in the night sky. Some believe it's a natural gap in the cosmic web. Others whisper it could be a scar left by something unimaginable, like another universe colliding with ours. Whatever the truth is, the Botas void stands as a reminder that most of the cosmos is nothingness. The Hell Planet, K2141b. 1.5 light-years away lies a planet where rocks rain from the sky, and oceans are made of molten lava. This world, known as K2141b, is locked in a deadly orbit. One side faces its star forever, scorched to over 3,000 degrees Celsius, while the other side is plunged into eternal darkness, cold enough to freeze nitrogen. Between them, hurricane winds of 5,000 kilometers per hour tear across the surface, carrying vaporized rock from the day side to the night side. It's a planet caught in a fiery loop, where mountains melt and the horizon glows like a furnace. If Dante's Inferno had a physical form, it would look like K2141b. The black hole at the center of M87, the mouth of hell. You've seen the photo, that glowing ring of fire, captured in 2019 by the Event Horizon Telescope. That's Messier 87's black hole, a supermassive monster 6.5 billion times the mass of the Sun. It sits at the heart of its galaxy, devouring everything that dares to come close. Gas, dust, even light itself spiral inward, forming a magnetic whirlpool of destruction. Cross the event horizon, and you're gone. Time slows, space folds. The laws of physics simply stop. If hell exists anywhere in the cosmos, it's here, where gravity crushes reality itself. PSRB 1257 plus 12 in the Dead Star System. 2,000 light-years away, a dead star still spins, a pulsar, the collapsed heart of a massive supernova, and around it, incredibly, orbit planets. But these aren't normal worlds. They circle a corpse, bathed in radiation that would vaporize any atmosphere in seconds. Scientists call them zombie planets, because they were born from death, forged from the wreckage of the explosion that killed their star. In a way, they're a cosmic paradox, proof that even in death, the universe still creates. The Galaxy Without Dark Matter, NGC 1052-DF2. In 2018, astronomers discovered something impossible, a galaxy with almost no dark matter. It's called NGC 1052-DF2, and it shouldn't even exist. Without dark matter to hold it together, its stars are drifting apart, slowly dissolving into the cosmic night. It's as if gravity forgot this place, a galaxy dying not with a bang, but with a whisper. The fastest spinning neutron star, PSRJ 1748-2446 AD. This star spins 716 times every second. Faster than a blender, faster than anything in the universe. It's a neutron star, the remnant of a supernova, a cosmic corpse so dense that a single teaspoon of it weighs 1 billion tons. If you stood on its surface, its gravity would crush you instantly, compressing your body into a layer of atoms thinner than paper. Neutron stars are the universe's ghosts, what's left when the light dies, but refuses to disappear. The Eridanus supervoid, the cold spot of the universe. And then, there's the Eridanus supervoid, a cold region of space that shouldn't exist. It stretches nearly 1 billion light-years across, a place so empty, even the cosmic microwave background is weaker there. Some scientists think it's just a random fluctuation. Others believe it might be the scar of another universe colliding with ours in the distant past. If that's true, then our universe might not be alone, and what lies beyond could be far stranger than anything we can imagine. The dark beauty of the universe. The scariest places in the universe aren't monsters or myths, they're real. They exist now, waiting silently in the dark. Each one a reminder of how fragile we are, and how powerful the cosmos can be. Because even in terror, there's beauty. And even in the darkest corners of space, there's still wonder. Imagine waking up tomorrow, and the sun is gone. The first moments. At first, it might seem like nothing happened. Why? Because light and gravity behave differently. Light takes about 8 minutes and 20 seconds to reach Earth. That means we'd still see the sun for almost 8 minutes after it's gone. Gravity also travels at the speed of light. So, after 8 minutes, Earth would lose the sun's gravitational pull and stop orbiting, moving in a straight line into the void of space. What happens to the planets? Once gravity disappears, planets don't just fall. They move in straight lines. Earth would drift into darkness, Jupiter's moons would fly off, and Saturn's rings could disintegrate. Our solar system would quickly become chaotic, while distant star systems remain unaffected. Fun fact insert. Earth is moving at 30 kilometers per second in its orbit. That's 108,000 kilometers per hour. Without the sun's pull, we'd just keep flying in that direction. Loss of light and heat. 8 minutes after the sun disappears, Earth plunges into total darkness. Day instantly becomes night. Temperatures start dropping rapidly. Within hours, surface temperatures could fall to minus 17 degrees Celsius, 1 degree Fahrenheit. Within a week, the average temperature could reach minus 70 degrees Celsius, minus 94 degrees Fahrenheit. And after a year, Earth might freeze to around minus 240 degrees Celsius, minus 400 degrees Fahrenheit. Effects on atmosphere and weather. Without the sun's heat, winds would eventually stop. The atmosphere would become still and extremely cold. Storms as we know them would vanish. The water cycle, evaporation, clouds, rain, would collapse. Earth would become a silent, frozen world. Oceans and ice. Oceans would slowly freeze, but deep layers might remain liquid due to Earth's internal heat. Some life could survive near hydrothermal vents on the ocean floor. Microorganisms, and maybe deep-sea creatures, could hold on for centuries, isolated under kilometers of ice. Effects on life. Without sunlight, plants die immediately and the food chain collapses. Humans would need to find ways to survive, underground, near geothermal heat, or using artificial light and energy sources. Most surface life wouldn't survive the first weeks. Long-term consequences. Over decades, Earth would drift through space, endlessly dark and cold. Oceans frozen, atmosphere thin and still, and chemical cycles stopped. We'd become a rogue planet, floating alone among the stars. Fun fact insert. Even without the sun, Earth's core remains hot, keeping some deep areas habitable for extremophiles. Life clinging on where sunlight can't reach. Human imagination in the universe. While our sun disappearing is catastrophic, life might exist elsewhere around other stars. Planets orbiting stable stars could still harbor warmth and life. It's a reminder of how precious our sun is, and how fragile life truly is. So, if the sun suddenly disappeared, Earth would quickly become a frozen, dark, and mostly lifeless planet, with maybe a few microorganisms surviving in the deep oceans. It's a chilling thought, and a reminder to appreciate the star that makes life possible. Mercury and Venus, the two worlds closest to the sun, have no moons at all. No natural satellites, no companions, nothing orbiting them. Why? The solar system's moon pattern. Moons are not rare. In fact, they're one of the most common features of planetary systems. Gas giants collect moons from massive disks of gas and dust. Planets capture passing objects. Giant impacts can create moons from debris. Our own moon likely formed after a colossal collision between Earth and a Mars-sized body. So statistically, Mercury and Venus should have moons, yet they don't. That makes them the exception, and exceptions always have a story. Mercury, too close to the sun. Let's start with Mercury. Mercury orbits incredibly close to the sun, only about 58 million kilometers away. At that distance, the sun's gravity is overwhelmingly powerful. The Hill sphere. Every planet has a region around it where its gravity dominates. This region is called the Hill sphere. For Mercury, that region is very small. So small that stable moon orbits are extremely difficult, even if Mercury captured a moon. It likely wouldn't last solar tides. The sun constantly pulls on anything near Mercury. Over time, this tidal force would destabilize a moon's orbit, pull it away, or cause it to crash into Mercury. Did Mercury ever have a moon? It's possible Mercury once had a moon, or several small ones. But simulations suggest they would have been stripped away by the sun, destroyed by impacts, or absorbed by Mercury itself. In short, Mercury lives too close to the sun to keep a moon. Venus, the strange twin of Earth. Venus is more mysterious. It's nearly Earth's twin in size and mass. It formed in the same region of the solar system. So why does Earth have a moon, and Venus doesn't? Venus's slow, backward rotation. Venus rotates extremely slowly. One day on Venus is longer than its year. It also spins backwards compared to most planets. This unusual rotation plays a key role. Tidal interactions. If Venus ever had a moon, tidal forces between the planet and the sun could have caused problems. Instead of stabilizing a moon's orbit, like Earth's moon does, Venus's slow rotation may have. Pulled moons inward caused orbital decay, led to collisions or ejections. A violent past. Another possibility. Venus once had a moon created by a giant impact, just like Earth. But later, massive volcanic resurfacing, extreme atmospheric evolution, or gravitational interactions with the sun may have destroyed or absorbed that moon. Venus's surface has been almost completely reset in the past, wiping out geological evidence. If Venus lost a moon, the planet may have erased all traces of it. Why Earth kept its moon? So why did Earth succeed where Mercury and Venus failed? Earth sits at the perfect distance, far enough from the sun with a large hill sphere and a fast rotation early in its history. This allowed Earth's moon to stabilize into a long-term orbit, slowly move outward, survive for billions of years. Mercury was too close. Venus was too unstable. Earth was lucky. What this tells us about planetary systems. Moon systems are fragile. They depend on distance from the star. Planetary rotation early impacts long-term gravitational balance. Even small changes can mean the difference between a planet with moons and a planet completely alone. Mercury and Venus remind us that planetary history is chaotic. What we see today is only the final chapter of a long, violent story. Mercury and Venus are moonless not because moons are rare, but because keeping a moon is hard. Mercury couldn't hold on to one. Venus likely lost it. And Earth? Earth simply got lucky. How many moons does Saturn have? As of today, Saturn has more than 140 confirmed moons, and the number keeps growing. Why does it keep changing? Because many of Saturn's moons are extremely small, irregularly shaped, difficult to detect from Earth. As telescopes improve, astronomers continue to discover new tiny moons orbiting Saturn. Some are only a few kilometers wide, barely more than cosmic debris. Saturn doesn't just have moons, it has an entire swarm. Saturn's powerful gravity. The first reason Saturn has so many moons is simple: gravity. Saturn is the second largest planet in the solar system and is about 95 times more massive than Earth. That enormous gravity allows Saturn to capture passing objects, hold onto weakly bound moons, prevent moons from easily escaping. Many of Saturn's smaller moons were likely captured long ago. Icy bodies and asteroids pulled in by Saturn's gravitational pull. But gravity alone isn't the full explanation. Saturn's perfect location. Saturn sits in a cosmic sweet spot. Far enough from the Sun that ice could survive moon formation was easier, yet close enough that objects from the early solar system frequently passed nearby. In the early solar system, space was chaotic, debris everywhere, constant collisions, objects flying in all directions. Saturn acted like a cosmic vacuum cleaner, pulling in anything that came too close. Some objects became moons, others broke apart, and that leads us to Saturn's rings. The connection between moons and rings. Saturn's rings and moons are deeply connected. Many scientists believe that. Some moons formed from ring material, some rings formed from destroyed moons. If a moon drifts too close to Saturn, powerful tidal forces can tear it apart, spreading debris into rings. At the same time, ring particles can slowly clump together, forming new moons over time. Saturn may be constantly recycling moons, destroying some and creating others. No other planet does this on such a large scale. Saturn's most amazing moons. Now, let's talk about quality, not just quantity. Titan is Saturn's largest moon and is bigger than Mercury. It has a thick atmosphere, lakes and rivers of liquid methane, complex organic chemistry. Titan looks like a frozen version of early Earth. Enceladus. Enceladus is small but extraordinary. It is covered in ice, spraying water into space, likely hiding a global ocean beneath its surface. This tiny moon is one of the best places to search for life in the solar system. Irregular moons. Saturn also has dozens of irregular moons with tilted orbits, strange paths, captured origins. Each one tells a story from the solar system's violent past. Why Saturn beats Jupiter. Jupiter is bigger than Saturn. So why doesn't it have more moons? Because Jupiter's gravity is too extreme. Its powerful gravitational and radiation environment ejects small moons, destabilizes fragile orbits, makes long-term survival difficult. Saturn is massive, but gentler. That balance allows moons to remain stable for billions of years. A brief history of Saturn's moon system. To really understand Saturn's moons, we need to go back over 4.5 billion years. When Saturn was forming, it was surrounded by a thick disk of gas, ice, and dust, similar to a miniature solar system. Inside this disk, larger moons like Titan likely formed first, smaller moons formed later, or from leftover debris. But Saturn's system never stayed calm. Over billions of years, moons migrated inward and outward. Some collided, some were torn apart, some were captured from elsewhere. What we see today isn't the original system. It's the result of constant change and reshaping. The Roche limit, where moons go to die. There's an invisible boundary around Saturn called the Roche limit. Inside this region, Saturn's tidal forces overpower a moon's gravity. Moons cannot stay intact, they begin to break apart. This is likely how parts of Saturn's rings formed, some moons were destroyed. Anything that crosses this line risks being pulled apart into billions of icy fragments. Saturn's rings may be the graveyard of ancient moons. Trojan and co-orbital moons. Saturn also has something very unusual. Some moons share orbits. These are called co-orbital or Trojan moons. For example, Janus and Epimetheus, they swap orbits every few years without colliding. This kind of orbital dance is extremely rare, very delicate, only possible in stable gravitational systems. It's another sign that Saturn's moon system is uniquely complex. Why we keep finding new moons. So, why are new Saturn moons still being discovered? Because many are incredibly dark, many are very small. Many orbit far from Saturn modern surveys use. Long exposure imaging, motion tracking, powerful data analysis. Each improvement reveals objects that were invisible before. In the future, Saturn may officially have hundreds of moons. What Saturn's moons teach us about planet formation. Saturn's moons aren't just fascinating, they're scientific gold. They help us understand how planets form, how moons migrate, how rings evolve, how habitable environments might emerge. Enceladus and Titan, in particular, are natural laboratories for studying chemistry, oceans, prebiotic conditions. By studying Saturn, we're learning how planetary systems everywhere might evolve. Saturn isn't just a planet with rings. It's a dynamic living system where moons are born, destroyed, captured, and reshaped. A system still evolving, still surprising us, still hiding secrets. The king of rings, the king of moons, and one of the greatest stories in our solar system. We're counting down the top 5 impacts of a galactic collision on our solar system. Impact number 1. Stars will scatter, but probably not ours. During a galactic collision, the gravitational pull of billions of stars will create chaotic motions. Stars will scatter, form streams, and sometimes get ejected from their galaxies entirely. But the space between stars is so vast that the likelihood of a direct collision with our Sun is astronomically small. Literally. Impact number 2. Gravitational chaos could affect orbits. The combined gravity of billions of stars can subtly tug on our solar system. While planets remain bound to the Sun, comet paths and distant objects in the Oort cloud could be disturbed. Over millions of years, this could slightly shift our position in the galaxy, changing the cosmic neighborhood we orbit through. The Oort cloud extends almost a light year from the Sun. Imagine how far gravity could nudge these icy bodies. Impact number 3. New waves of star formation. As galaxies collide, gas clouds compress under extreme pressure, triggering massive bursts of star formation. Thousands of new stars could appear, some with planets orbiting them. This will create a spectacularly bright night sky, though our solar system remains untouched. These starbursts can produce thousands of new solar systems in just a few million years. Blink, and new stars are born. Impact number 4. Supernovae could increase radiation. Massive stars created in starbursts live fast and die young as supernovae. These explosions release intense radiation, which could reach our solar system. While Earth's atmosphere shields us from most cosmic radiation, strong bursts could affect satellites, space probes, and, in extreme scenarios, even upper atmospheric chemistry. Impact number 5. Our solar system might join a new galactic neighborhood. After billions of years, the Milky Way and Andromeda will merge into a single elliptical galaxy. Our solar system might find itself in a completely new neighborhood, surrounded by stars it never orbited near before. This could slightly change the cosmic radiation environment and provide a dazzling new view of the night sky for future observers. Imagine looking up and seeing thousands of new stars where there used to be none. What would that feel like? A moment of cosmic perspective. It's important to remember that galactic collisions don't happen like explosions in movies. They unfold slowly, over hundreds of millions and even billions of years. From the perspective of our solar system, this would feel less like a disaster, and more like a gradual change in our place in the universe. For most of this process, life on Earth wouldn't even notice what's happening on a galactic scale. Days would still pass, seasons would still change, and humanity might look up at the sky without realizing it's quietly transforming. What makes this event truly fascinating isn't destruction, it's scale. Entire galaxies reshaping themselves, while tiny planetary systems like ours continue their journey, almost untouched, through a universe that never stops evolving. Bonus facts and fun speculations. Despite all this cosmic chaos, life on Earth is likely safe. Direct star collisions are nearly impossible due to vast distances. But the night sky will look different, and for astronomers of the future, the universe will be a very dynamic place. Some simulations suggest our sun could slowly drift into a new, quieter region of the merged galaxy, changing our cosmic surroundings without threatening the planets themselves. The biggest change wouldn't be destruction, but transformation. Over time, the sky would gradually fill with unfamiliar stars and glowing regions of new star formation. For future astronomers, the universe would no longer feel distant or static, but alive, evolving, and constantly changing. Galactic collisions remind us how dynamic and ever-changing the universe is. From subtle orbital shifts to dazzling waves of new stars, the cosmos never stands still. What are exoplanets? An exoplanet is simply a planet that orbits another star. The first confirmed one was discovered in 1995, around a sun-like star called 51 Pegasi. Back then, it was revolutionary. Today, we've found over 5,600 confirmed exoplanets, with thousands more waiting for verification. They come in every shape and size. Hot Jupiters, gas giants orbiting so close to their stars that their years last only a few days. Ice worlds, frozen spheres orbiting faint red dwarfs. And Earth-like planets, small, rocky, and possibly covered in oceans. Each new discovery pushes the boundaries of what we thought was possible, and reminds us how diverse the universe truly is. The Golden Zone. Not every planet can host life. For that, it must lie in a very special place, the habitable zone. This is the distance from a star where temperatures are just right for liquid water to exist. Too close, and oceans boil away. Too far, and everything freezes solid. Earth sits perfectly in this Goldilocks zone, and scientists are searching for other worlds that do too. Planets that could have the same balance of warmth, light, and atmosphere that made life possible here. But being in the habitable zone doesn't guarantee habitability. It's just the first clue in a much larger cosmic puzzle. Tools of discovery. Finding exoplanets isn't easy. They're tiny and lost in the blinding glare of their stars. So, how do we find them? We use light. The transit method, used by NASA's Kepler and TESS telescopes, detects tiny dips in starlight as a planet passes in front of its star. The radial velocity method measures the star's subtle wobble caused by the planet's gravity. And now, with the James Webb Space Telescope, we can do something incredible. We can study their atmospheres. By splitting the starlight that passes through an exoplanet's atmosphere, Webb can identify molecules, water vapor, methane, carbon dioxide, even potential signs of life. Each chemical fingerprint tells us something about that world, what it's made of, how it formed, and maybe whether it could support life. Promising worlds. Among thousands of discoveries, a few stand out. Worlds that have captured scientists' attention and imagination. K2-18b, about 120 light-years away. It's larger than Earth, but smaller than Neptune. Webb's data revealed traces of carbon-bearing molecules and possibly dimethyl sulfide, a chemical produced by life on Earth. It's not proof, but it's the closest we've come. TRAPPIST. One system, 7 rocky planets orbiting a small red dwarf. 3 of them sit in the habitable zone. Imagine 3 Earths side by side, orbiting one faint red sun. LHS-1140b. A potential ocean world, covered entirely in water under a thick atmosphere. And then there's Kepler 452b, sometimes called Earth's cousin. It's 60% larger than our planet, orbits a star much like the Sun, and might have mountains, clouds, and continents. Each of these worlds offers a new perspective, a new what if. New missions, new eyes. The golden age of exoplanet discovery is just beginning. ESA's Plato mission, launching soon, will search for Earth-like worlds around Sun-like stars with unprecedented precision. Ariel will study hundreds of exoplanet atmospheres, decoding their chemical fingerprints. Future concepts like LUVOIR and HABEX could directly image other Earths, not just dots of light, but blue worlds with clouds, continents, and maybe life. Imagine seeing a real photograph of another Earth, oceans glimmering in alien sunlight. That's the dream scientists are working toward. What does life really mean? But when we say life, what do we really mean? Are we looking for creatures like us? Or just the simplest microbe? Here on Earth, life thrives in the strangest places. In boiling acid pools, beneath frozen glaciers, even miles underground. So, if life can survive here, it could exist almost anywhere. Maybe beneath the ice of distant moons. Maybe in the clouds of alien worlds. Maybe in forms we can't even imagine. What finding life would mean. The search for exoplanets isn't just about science, it's about perspective. Each discovery reminds us that our world is one of billions, a small, fragile oasis in an endless cosmic ocean. If we ever find proof of life beyond Earth, it won't just change astronomy, it will change us, because in that moment we'll know we were never alone. Signs of life, how we'll know. So, how will we actually know if life exists out there? How can we tell from hundreds of light years away? The answer is hidden in light itself. Every planet reflects and absorbs starlight differently. When that light passes through a planet's atmosphere, it carries clues, fingerprints of the gases within. On Earth, our atmosphere is filled with oxygen, nitrogen, and traces of methane, all produced by living organisms. So, if we ever find another world with a similar chemical mix, it could mean we're not alone. But it's not that simple. Life could be completely different elsewhere, using chemistry we've never seen. That's why scientists are now building AI models that can recognize biosignatures, subtle patterns that might hint at biology, even if it doesn't look like ours. In the near future, telescopes like LUVOIR might even take direct images of alien skies, showing the colors of sunsets on another world, and maybe the faint glimmer of something living beneath them. The future of humanity among the stars. Our search for exoplanets isn't just curiosity, it's preparation. Every world we discover teaches us more about how fragile our own planet is. and how rare the right conditions for life can be. Maybe one day humanity will leave Earth, not to escape it, but to expand our story among the stars, to build a second home under another sun, to explore, not as conquerors, but as explorers of the unknown. Projects like Starshot and interstellar probes are already being designed to reach nearby systems like Alpha Centauri, our first steps into the wider galaxy. If we can one day travel across light years, imagine what we might see. Cities beneath alien skies, forests of colors we've never dreamed of, and oceans reflecting a foreign sun. It may take centuries, but it starts now, with every telescope pointed toward the stars. What is a year? On Earth, a year lasts 365 days. That number feels natural, almost absolute. But it isn't. Every planet follows its own path, its own speed, its own rhythm in the dance around the sun. Some worlds race, some crawl, some take so long that a single year could last multiple human lifetimes. Today, we compare them all. The inner planets. 1. Mercury, the fastest year. Mercury orbits faster than any other planet. 1. Mercury year? Just 88 Earth days. That means if you lived there, you'd celebrate a birthday every 3 months. But don't get too excited. The sunrises would only happen every 176 days. On Mercury, a day is longer than its year. 2. Venus, the slow paradox. A Venus year lasts 225 Earth days, but Venus rotates so slowly that one Venus day is longer than one Venus year. Time stretches strangely there. If you stood on its toxic surface, the sun would move across the sky, in reverse. 3. Earth. Our familiar year, 365 days. The rhythm of our seasons, our holidays, our memories. But Earth is not normal. It's just one example, one orbit, in a universe full of variation. 4. Mars. The longer year. Mars takes 687 Earth days to complete one orbit, almost 2 Earth years. Spend a year on Mars, and when you returned home, 2 Earth birthdays would have passed. The gas giants. 5. Jupiter, the giant. With a long journey. Jupiter is huge, the largest planet in the solar system. But size slows nothing. Its distance from the Sun does one Jupiter year lasts 11.86 Earth years. Imagine a child born on Jupiter's new year. They wouldn't see their first birthday until middle school. 6. Saturn, time behind the rings. Saturn orbits far beyond Jupiter. Its year, 29.4 Earth years. An entire generation passes between Saturnian New Years. Cold, slow, distant. Saturn feels the weight of time like no other world. 7. Uranus, the tilted year. Uranus is tilted on its side, rotating almost horizontally. Its seasons last decades, and its orbit, 84 Earth years. If you were born on Uranus, you'd be lucky to see your first full year before you died. 8. Neptune, the longest year in the solar system. Neptune is the farthest major planet from the Sun. Light from the Sun takes more than 4 hours to reach it. A Neptunian year lasts 164.8 Earth years. No human has ever lived a full Neptune year. No human ever will. Beyond Neptune. If we extend our journey to dwarf planets and distant objects, time becomes even stranger. Pluto, 248 Earth years. Eris, 558 Earth years. Sedna, 11,400 Earth years. Civilizations could rise and fall before these worlds complete a single orbit. What this teaches us about time. We think of time as universal, steady, predictable, absolute. But a year is not a cosmic constant. It's a story each world tells, a measure of its path through space. On some planets, years fly by in weeks. On others, a single year is longer than human history. Time is not the same everywhere, and neither are we. Every planet lives by its own cosmic calendar. Every world moves to its own rhythm. And as we explore the universe, we discover that time itself is as diverse and mysterious as the worlds that drift through it. What is 3I Atlas? 3I Atlas is unlike any comet we've observed before. Ordinary comets are bound by the sun's gravity, circling our solar system in predictable paths. But 3I Atlas is different. Its course is not anchored here. It comes from the depths of another star system, journeying through light years of darkness, only to briefly grace our cosmic neighborhood before vanishing again. It carries ice, dust, and complex organic molecules, remnants of planetary systems far beyond our own. Among them, water, possibly identical in composition to the water that once swirled around alien suns billions of years ago. Water is a messenger from other worlds. Water is life's most precious ingredient, yet its origins remain a cosmic mystery. On Earth, the isotopic signature of water does not perfectly match what we would expect from our own solar system. Could it be that some of it came from the stars themselves? By studying the ice, dust, and gases of 3I Atlas, scientists can glimpse the materials that shaped other planetary systems and perhaps understand how water, the seed of life, arrived on Earth. The voyage across the galaxy. Imagine the journey of a single comet, ejected from its parent star system millions of years ago. It drifts through the cold, empty void, undisturbed, until it encounters the sun. Here, it briefly becomes visible, a solitary traveler illuminating the cosmic stage. Each grain of dust, each molecule of ice, carries a story billions of years in the making. These fragments of distant worlds may hold the key to understanding life's cosmic origins. The science behind the mystery. Astronomers turn the universe's most powerful telescopes toward 3I Atlas. They study its composition, measure isotopic ratios, and track its trajectory. Every observation is a message from another star system, a whisper of the cosmos's deep history. Even the smallest particles from 3I Atlas carry clues. They may reveal whether the water in our oceans, the very foundation of life, was delivered by interstellar travelers. Implications for life beyond Earth. If water can travel between stars, might life itself? The theory of panspermia suggests that life can spread across the galaxy on comets or asteroids. 3I Atlas brings this possibility to life, reminding us that the seeds of life may wander through the stars, waiting to land on fertile worlds. This comet is more than ice and rock. It is a testament to the interconnectedness of the cosmos, showing that Earth is part of a vast galactic network. Mysteries of interstellar visitors. 3I Atlas will eventually depart, returning to the dark reaches of space. Its fleeting visit, however, reminds us that the universe is alive with motion, with hidden stories, and mysteries that defy imagination. One visitor from the stars may hold answers to questions older than humanity, the origins of water, life, and our place in the galaxy. Reflecting on cosmic origins. Every comet, every interstellar traveler, is a fragment of the universe's memory. 3I Atlas reminds us that Earth is not alone. The molecules in our oceans may have danced around distant suns long before our planet existed. In the silent vastness of space, water tells a story, if we are willing to listen. And in that story, we may find the echoes of life itself. The cosmic connection. 3I Atlas is not merely a visitor, it is a messenger. Its icy trails may carry hints of the beginnings of life, reminding us that the universe is more interconnected than we can imagine. Every particle, every drop of water, could have a story that began around a distant star, millions of years before Earth was born. Fact 1. The universe is expanding faster than we thought. Since the Big Bang, the universe has been expanding. That in itself is incredible. Galaxies drifting apart, carried on the fabric of space itself. But here's the mind-blowing twist. The expansion is actually speeding up. Instead of slowing down, as gravity should be pulling everything together, galaxies are racing away faster and faster. Why? Scientists believe it's due to something mysterious we call dark energy. We don't know what it is. We don't know why it's there. All we know is that it makes up about 68% of the universe, and it's literally pushing reality apart. Fact 2. More stars than grains of sand. Next time you're on the beach, pick up a handful of sand. Each tiny grain represents a star, but even that won't do the cosmos justice. Astronomers estimate there are 200 billion galaxies, each holding hundreds of billions of stars. That means the universe has more stars than all the grains of sand on Earth's beaches combined. Each one of those stars could have planets, and each of those planets could hold secrets we've never even imagined. Fact 3. Black holes can sing. Black holes are some of the strangest objects in existence. They bend light, stretch time, and swallow matter whole. But did you know they can also sing? In 2003, NASA discovered that a black hole in the Perseus galaxy cluster was vibrating space in such a way that it produced sound waves. The pitch? A B-flat, 57 octaves lower than the human ear can hear. Imagine a note so deep, so powerful, that it echoes across hundreds of thousands of light years. A cosmic hum in the silence of space. Fact 4. Neutron stars, the most extreme objects. When a massive star dies, it can collapse into a neutron star, a city-sized object with the mass of 2 suns. 1 teaspoon of neutron star material would weigh 1 billion tons on Earth. And that's not all. Some neutron stars, called pulsars, spin hundreds of times every second, blasting out beams of radiation like cosmic lighthouses. These stars are so extreme that they warp physics itself, truly the monsters of the universe. Fact 5. Looking at stars means looking back in time. Every time you look at the night sky, you're not just seeing stars, you're seeing history. Light takes time to travel. The light from the sun takes 8 minutes to reach us. From the nearest star, it takes over 4 years. From distant galaxies, billions of years. That means some of the stars you see at night might not even exist anymore. You're looking at ghosts of the past. In a very real sense, telescopes are time machines. Fact 6. Space has a smell. You might think the vacuum of space is empty and scentless, but astronauts have reported something surprising. After spacewalks, when they re-enter the spacecraft, their suits smell like burnt steak or welding, fumes. This comes from high-energy particles in space interacting with the suits. So yes, the universe has a smell, and apparently, it's barbecue-flavored. Fact 7. Supermassive black holes control galaxies. At the center of nearly every galaxy, including our Milky Way, there lurks a supermassive black hole. The one at our core, Sagittarius A, is 4 million times the mass of the Sun. These giants don't just sit there. They influence the motion of billions of stars, shaping the very structure of their galaxies. Without them, galaxies like ours might not even exist. They are the hidden rulers of the cosmos. Fact 8. On Jupiter and Saturn, it rains diamonds. Storms on Earth bring water, snow, and sometimes hail. But on Jupiter and Saturn, the storms create something far stranger: diamond rain. Here's how it works. Intense lightning storms turn methane into soot. As it falls, pressure turns it into graphite. Deeper down, the pressure becomes so extreme that the graphite crystallizes into diamonds. Imagine billions of diamonds raining through alien skies. Forget mining. Saturn might just be the universe's biggest jewelry factory. Fact 9. 95% of the universe is invisible. Here's a fact that will truly bend your mind. Everything you see, stars, planets, galaxies, people, everything, makes up only 5% of the universe. The other 95%? Dark matter and dark energy. We don't know what they are. We can't see them. We can't touch them. But they're out there, shaping galaxies, driving expansion, and literally making up most of reality. In other words, the universe we know is just the tip of the iceberg. Fact 10. The universe will have an end. Everything that begins must have an end, even the universe. Scientists have three main theories about how it might all end. The Big Freeze. The universe keeps expanding forever. Galaxies drift apart, stars die, and eventually, the cosmos becomes a cold, dark wasteland. The Big Rip. Expansion accelerates so much that galaxies, stars, planets, and eventually even atoms are torn apart. Reality itself unravels. The Big Crunch. Expansion slows and reverses. The universe collapses back into a single point, possibly sparking another Big Bang. No one knows which will happen, but what's certain is that the universe is not static. It has a story, and one day it will have an ending. Fact 11. The largest structure in the universe. The universe is full of galaxies, clusters, and cosmic webs, but the single largest structure ever discovered is the Hercules Corona Borealis Great Wall. It's not a wall like we think on Earth, but a colossal galactic filament stretching over 10 billion light-years across. That's so massive, it shouldn't even exist according to some models of cosmology. Yet there it is, a titanic reminder of how small we really are in the grand cosmic architecture. Fact 12. The oldest light in the universe. When we look deep into space, astronomers can detect a faint glow everywhere. The cosmic microwave background radiation. This is the oldest light in existence, left over from the Big Bang nearly 13.8 billion years ago. It's like an afterglow, a baby picture of the universe when it was just 380,000 years old. By studying this faint light, scientists unlocked secrets about the origins of everything we see today. Fact 13. Rogue planets, worlds without suns. Not all planets orbit stars. Some are cosmic orphans, rogue planets, wandering alone in the darkness of interstellar space. Astronomers estimate there could be billions of these dark worlds in our galaxy alone, floating freely without the warmth of a sun. Some might even have atmospheres or underground oceans, warmed by their own inner heat. Imagine life evolving on a planet with eternal night. Fact 14. There could be infinite universes. What if our universe isn't the only one? Some theories in physics suggest the existence of a multiverse, an infinite sea of universes, each with its own laws of physics. In one, gravity might be stronger. In another, stars might never form. And somewhere, there could even be universes eerily similar to ours. We don't yet know if this is true, but if it is, our entire universe may just be one bubble in a vast cosmic ocean. Fact 15. The universe has no edge. When we think of the universe, we imagine it must have an edge, a place where space ends. But physics tells a different story. The universe could be finite but unbounded, curving back on itself like the surface of a sphere. If you traveled in one direction long enough, you might eventually return to where you started. Or it could be infinite, stretching endlessly with no boundaries at all. Either way, the reality is more mind-bending than we can truly comprehend. The universe may have no edge and no outside. These are the top 5 most mind-blowing space discoveries of 2025. Number 5. The new Earth-like exoplanet, Kepler X-9b. Let's start with number 5. A planet that might just feel a little too familiar. Astronomers recently discovered Kepler X-9b, a rocky world orbiting a star 120 light-years away. What makes it so incredible? Its temperature, size, and atmosphere are eerily similar to Earth's. Scientists believe this planet could have liquid water, and possibly the chemical ingredients for life. Unlike most exoplanets we've found, Kepler X-9b orbits in what's called the Goldilocks zone. Not too hot, not too cold. Could it be another home for humanity one day? That's the question scientists are now racing to answer. Number 4. The black hole that changes shape. At number 4, a black hole that's breaking all the rules. Using data from the Event Horizon Telescope, astronomers detected something no one expected. A black hole whose shape appears to change over time. Normally, black holes are perfectly round, invisible shadows surrounded by glowing disks of gas. But this one seems to wobble and morph, as if it's breathing. Some scientists think this could be evidence of a spinning magnetic field, or even 2 black holes merging in slow motion. Whatever it is, it's rewriting our understanding of how black holes behave and what might be hiding inside them. Number 3. Strange radio signals from the edge of the universe. Number 3 is pure mystery. A repeating radio signal coming from 11 billion light-years away. Fast radio bursts, or FRBs, have puzzled scientists for years. They're like cosmic heartbeats that flash for milliseconds, then vanish. But this new signal is different. It repeats every 16 days, with a rhythm too precise to be random. Is it a new kind of neutron star? A magnetar spinning in a binary system? Or something else? No one knows for sure. But one thing's certain. The source is so distant, it's as if the universe itself is whispering from the past. Number 2. The most detailed image of a distant galaxy. Number 2 will blow your mind visually. In 2025, the James Webb Space Telescope captured the clearest ever image of a galaxy, located more than 13 billion light-years away. This galaxy formed just 300 million years after the Big Bang. And yet, it already shows massive star clusters and complex structures. That means galaxies in the early universe evolved faster than anyone expected. For astronomers, it's like opening a time capsule, a snapshot of creation itself. Number 1. Signs of dark matter interaction. And finally, number 1. The discovery that could change physics forever. For decades, dark matter has been invisible. We know it's there, but we've never seen it, never touched it. Until now. In early 2025, a team of researchers at CERN detected anomalous particle collisions, tiny energy patterns that may indicate dark matter particles interacting with ordinary matter. If confirmed, this would be the first real evidence that dark matter isn't just a theory, but a fundamental part of our universe's structure. We might be standing on the edge of the biggest scientific breakthrough since the discovery of the Higgs boson. Every one of these discoveries reminds us the universe isn't done surprising us yet. For every answer we find, 1,000 new questions appear. And that's what makes space so endlessly fascinating. What if humanity tried to celebrate Christmas in space? Christmas without time. The first problem: space has no day, no sunrise, no December 25th. On Earth, we know exactly when Christmas starts. But in space, on the ISS, there are 16 sunrises and sunsets every day. A day on Mars is longer. Deep in space, there are no days at all. Near a black hole, time slows dramatically. So Christmas might happen every 45 minutes on the ISS, or stretch for days near a black hole. Astronauts joke, in space, Christmas happens whenever the crew agrees. So on a spaceship, the holiday would start by ship time, and on another planet, according to its own cosmic clock. Christmas tree in space. A normal Christmas tree doesn't work in zero gravity. It floats, it spins, the decorations drift away, so humanity would need new space-style Christmas trees. Option 1. A holographic Christmas tree. Floating light beams, shape-shifting ornaments. No mess, no gravity needed. Option 2. A magnetic wall-mounted tree metal surface. Magnetic ornaments levitating nearby. Option 3. A plasma Christmas tree. A glowing plasma sculpture inside a protective field. A literal fire tree inside a starship. And beyond the windows, a real cosmic decoration. Galaxies, nebulae, and star clusters. Snow in space. Believe it or not, space has snow. Not like Earth snow, but close. Cosmic snow number 1. Ice particles around comets. As comets warm near the sun, jets of gas erupt, releasing ice crystals, a kind of cosmic snowfall. Cosmic snow number 2. Methane snow on Titan, Saturn's moon. Titan has winter storms of methane and ethane. Imagine Christmas morning with orange skies and methane snowflakes. Cosmic snow number 3. Carbon snow on Europa Black. Soot-like flakes falling onto a bright, icy world. If humans celebrated Christmas across the solar system, each snow season would be different. White snow, black snow, or chemical snowstorms. Christmas music in space. In space, sound doesn't travel. No air, no sound waves. Jingle bells in open space, where there's total silence. So music would only exist through headphones, through bone conduction speakers, or through the ship's internal audio system, and near a neutron star. Due to gravitational redshift, music would sound lower, slower, as if stretched by gravity itself. Imagine Christmas songs warped by the fabric of spacetime. Christmas lights. Earth's holiday lights are beautiful, but space has far more spectacular decorations. The Christmas Tree Nebula, NGC 2264. A real nebula shaped like a cosmic tree. Auroras on Jupiter brighter, bigger and more powerful than Earth's. Red giant stars, massive glowing ornaments across the galaxy. The Milky Way, a 100,000 light-year-long natural light garland. If Christmas took place on another planet, the cosmos would become the decoration. Gifts in space. Astronauts on the ISS have tried celebrating small holidays, but even giving gifts is a challenge. Boxes float away. Wrapping doesn't stay on ribbons, unravel in midair. So gifts would need Velcro attachments, vacuum-sealed wrapping, 3D printed packages. Opening presents would look like slow motion, tiny pieces of wrapping drifting everywhere. The first real space Christmas. Imagine humanity living on Mars, the Moon, and interstellar ships. A space Christmas would become a symbol of how far we've traveled, of traditions carried across planets of unity beyond Earth. The most breathtaking places to celebrate: a Mars orbital station, a tiny blue sun shining over a red planet, a lunar base with Earth in the sky, glowing like a giant ornament, an interstellar starship where the crew celebrates while drifting between the stars. Christmas isn't about a date on the calendar or a place on Earth. It's a moment created by people, a reminder of who we are. And one day, when humanity becomes a multi-planetary species, Christmas will be the first holiday we take with us to other worlds. If Christmas happened in space, it would still feel magical, just a little more cosmic. If you enjoyed this journey of the universe, don't forget to like, subscribe, and explore more cosmic mysteries.